So welcome students, and in this video we are going to talk about the direct method of Lyapunov to show stability of a system. Okay, so first of all we are considering this system, the nonlinear system. Consider the nonlinear system. What is the system? X prime equals to f of x. Is it okay? Now the thing is this, see, we want to talk about the stability of this particular system. Yes, so let's just suppose that for now, suppose B star, okay, is the equilibrium point of this system. So what do I mean by this? I mean equilibrium point of this system. If you remember, we talked about this in the last video also. What is an equilibrium point? So basically f of B star is 0. Yes, okay, so that is there. So we are supposing that B star is the equilibrium point of this system. Of course B star is in Rn, right? So where we are assuming f is from omega subset of Rn to, let's say, some, I don't know, maybe Rd. Yes, okay, let's just suppose that. So basically B star is in omega, we are assuming it like that. Okay, now the thing is this, see, the question is we want to analyze the stability of the equilibrium. Okay, so the question is this, question is the equilibrium point stable? Equilibrium point, so in this case B star, stable. Okay, now, so see, when I say equilibrium point, you do realize that, let's say, xt, if I am assuming it to be B star, okay, for all t, yeah, then what happens is, so basically the constant vector xt, yeah, for all t, then what happens is, what is x prime of t? This is 0, yes, because this is constant, and that is nothing but f at the point B star. Okay, so you do realize that B star actually is a solution of this problem. If B star is an equilibrium point, that actually turns out to be a solution of the problem also. Okay, so essentially the question is this, we want to see that whether it's a stable equilibrium or not. B star that is, yeah. Okay, so here we looked at in the earlier videos, we have talked about stability under certain conditions. We know that there exists stability. Okay, Lyapunov has a different idea. This is called Lyapunov's direct method. Okay, there are some advantages of using this method to show stability. So what are the advantages? So first of all, the method which I am going to show. Okay, so what are the advantages? So first of all, you see, this particular method, okay, it is, I mean, if you want to, so it is very useful if one wants to derive global solutions, results. Okay, and also, you see, in the earlier cases you have seen that it depends on the the asymptotic stability of some equilibrium, that depends on what is the eigenvalue. So basically, let's say if eigenvalue is 0 and all, we really can't say anything, right? So here also the thing is, the asymptotic stability, let me write it like this, asymptotic stability, okay, of an equilibrium, okay, in which one or more, okay, so maybe I can write it, or more eigenvalues of the Jacobian have 0 real part. Okay, have zero real part. So the thing is this, see, in the earlier this thing video we have seen that if you have, I mean, if the thing is, if you look at the Jacobian matrix and one eigenvalue or more is has a zero real part, then we really can't say anything about the stability of the system, right? Okay, and the stable manifold theorem also, we know that it does not hold. So what we can do here is this, see, in this sort of situation also, if you can find, so essentially here the whole point is this, I will define something called a Lyapunov function. If you can find a Lyapunov function, then I mean, it's very easy. Okay, life is very easy. You can actually show the asymptotic stability. Okay, so now the thing is, I'm going to define something called a Lyapunov function. Okay, right. So first of all, you see, we are going to, so definition. Okay. Okay, so first of all, let L, I'm defining a function, let L, okay, from omega, okay, maybe I can do it in a different way. Okay, let me do it this way. Omega 2r be a real valued function, be a real valued function, omega 1 valued function which is defined on a open neighborhood of B star. Okay, so what is B star? B star is the equilibrium point. If you remember, B star is the equilibrium, that is what we are assuming. Okay, and this neighborhood we are calling it as an omega, which is containing omega 1, which is contained in omega. So you understand what I'm trying to say. See, of course, B star, as I told you, B star is contained in omega, right? Because otherwise f of B star is not defined, right? Okay, now what I am doing is this, since omega is open, that is assumed, so we will assume that omega is open. So since omega is open, what happens is, around any point you can actually talk about the open neighborhood, right? So we talk about a neighborhood, let's say omega 1 is a neighborhood, okay, and neighborhood of what, which point? B star. Yes, and we are defining the function L, which is defined on that neighborhood, okay, omega 1, and it's basically a real valued function. Is it okay? And what are the properties? So we want, let be defined on an open neighborhood of B star, say omega, such that L is continuous on omega 1 and it is C1 on omega minus 0. Is it okay? So basically I want continuity, sorry, not 0, B star. So I want continuity everywhere, and then I want just the continuous differentiable property everywhere in omega 1 minus the B star point. Okay, now L, so I am starting out with this, such a real valued function which is continuous in some neighborhood of B star, and this C1 in some, the, how do I put it, the neighborhood minus the B star. So in that neighborhood minus B star, everywhere it is C1. So L is said to be Lyapunov function, Lyapunov function if it satisfies some properties. If, okay, right, it satisfies if okay, Lyapunov function, maybe I should write it like this, Lyapunov function for the system, let's just call this system 1, for the system 1 near the equilibrium B star, okay, if the following holds. Okay, so let me write down the following thing. The first point is this: for all x in omega minus B star, yeah, we want gradient of L x acting at f of x, this should be less than equal 0. Is it okay? And I will explain what all of this means. Let me first write it down. And the second part is this: for all x in omega 1, okay, L of x is dominated by L of x dominates L of b star with equality only at x equals to b star. Is it okay? So essentially what I am looking for is this property, the b property. It basically says that b star has to be a strictly minima of L. Is it okay? So see, the thing is this: what we are trying to do is this. We know that there is an equilibrium point, right? Let's say b star is the equilibrium point. Yes. Now, so let's say b star is the equilibrium point. Okay, and this is in some omega. Yeah. So first of all, we identify a neighborhood omega 1 which is contained in omega, right? Neighborhood of b star. Now in this neighborhood I am defining a function v. Yeah, I am defining a function v, L. This function we are calling it as a Lyapunov function, and this is defined from this omega 1 to r. Yeah, what are the properties? It is continuous everywhere here, and it is C1 everywhere except at the point b star. Okay, right. Okay, now the thing is this: you see, we will call such a function as a Lyapunov function when first of all, you see, a property is there. I will explain what a means, but let's look at b. B basically says that the b star at the point b star, the value of L should be least. You understand? So b star has to be a strict minima of L over omega 1. So let's just put it this way: what are the meaning of this particular two properties? The b implies that b star, okay, the condition b implies that b star, the point b star, okay, is a strict minima, is the strict minima, not a, is the strict minima, is the strict minimum of L, okay, over omega 1. Is it okay? Yeah, so that's your b. Now the thing is, this is the b, so this is very important, strict minima. I will show you that why it is important. We cannot, I mean, omit this strict part. And what does a imply? What does a imply? Let's look at this. See, it says that the gradient of Lx acting at f, the dot product of that has to be less than equal 0. What does it mean? So let's look at this. See, d dt, let's look at d dt of L of xt. Is it okay? See, xt is somewhere in omega 1, right? Okay, let's say xt is in omega 1. So I am defining L of xt and I am taking the derivative. Let's just do that. See, L is c1, right? L is c1. So basically, if I take the derivative by chain rule, that will be gradient L acting at x of t, and then by chain rule, the derivative of this thing, which is x prime of t. Is it okay? Now, what is gradient L at the point x of t? This is nothing. This is fine. And what is x prime t? X prime t, you see, xt is a solution so of this problem. So xt is f of xt, right? X prime equals to f of xt. So it is f of x of t. Is it okay? So this is nothing but this is what we are writing as gradient of Lx acting at f of x. Is it okay? Yeah. Now you see, this d dt of Lxt is essentially this, and we are assuming that this is less than equal 0. It means that the derivative of L is decreasing, yes, along this trajectory. So basically it means that the derivative of L, okay, x along the trajectory, you see, it is saying that along this x of t is not for every point. If you go, see, let's say there is a x of t, okay, which converges towards b star, right? So if you move along that route around that curve, okay, towards B star, then and what does L do? So L is taking minima at B star, okay, and it is decreasing around that along the path, okay. So along a trajectory xt of x prime equals to f of x. I hope I can make you understand what's going on here. So essentially, you see, B star is the equilibrium point, right? So let's say you have a curve, okay, which solves. So basically, which is the solution of x prime equals to f of x, right? And the thing is, we are constructing a function L such that at the point B star, L is minima, and while it is approaching B star, the curve approaching B star, L along that curve is actually non-increasing. Is it okay? That's what it is saying. Yeah. So it is derivative of along is non-negative, essentially, non-positive. Sorry, non-positive, which actually implies that the Lx is non-increasing along any trajectory. So which means L of x is non-increasing along any trajectory of x prime equals to f of x. I hope this is clear to you now. Okay, fine. So the thing is this, what we did is we defined a particular kind of function which has some properties, okay. Now the question is this, what is so special about this? Why, what can we do with this? So this is the theorem which will actually guarantee that once if you have a system with a Lyapunov function, it is going to be Lyapunov stable. So basically the equilibrium is going to be stable, okay, stable in that sense. The last video we talked about, right, stability, exactly in that sense, okay. So if x prime equals to f of x admits a Lyapunov function, okay, L of x near B star, is it okay? Then the equilibrium B star, then the equilibrium is Lyapunov stable. I hope this is fine. Yes. Okay. So let's look at the proof of this. Okay. See. So first of all, again, what the thing is this is very easy. Okay. What it is saying is this: if you want to show that the equilibrium is Lyapunov stable, all you need to do is you just have to find out a Lyapunov function. That's what it is saying. Okay, very, very simple statement. Okay, but very powerful. So how do I prove it? So let's start with, let V be a neighborhood of B star. Okay, V be a neighborhood of B star. So B star is our equilibrium, right? Okay, now and we are just assuming that it is given. Okay, now you see, you choose a radius delta, okay, small, such that the ball with center at B star and radius delta, the closure of that ball, okay, is containing omega 1 intersection V. Is it okay? I can of course do that, right? It's very easy. Okay, now you see, the thing is why I am interested in this ball, because what I can do is, since this is compact, I can talk about the minima of this L of x, okay, over this x minus V star equals to delta over the boundary. You see, this ball, there is an interior and there is a boundary, right? Boundary is a compact set. Of course, the whole ball is a compact set, but the thing is, the boundary is also a compact set. What we are doing is, basically, we are taking the minimum of L over the boundary, right? On the boundary, let's just call that L, alpha. Why does it exist? This exists because L is assumed to be continuous, right? So continuous function on a compact set assumes a minima. So that's your alpha, right? Now, one second. I hope this is fine. What I wrote. Continuous function. Yeah, fine. And of course, alpha will be greater than L of B star. I hope this is clear. Why? Because B star is the minimum of L on that omega 1, right? Omega 1. And since this ball is on omega 1, okay, so alpha has to be greater than L of B star because L B star is the minima. Okay, now I will define a new function set. Sorry, V1. This is a set of all those x in B, the ball which you are talking about, such that L of x is strictly less than alpha. Let's just look at that set. Is it okay? V1 is a set of all those x such that the ball with center B star and radius delta such that Lx less than alpha. This is our V1. Is it okay? Now, if B is in V1, I will define a new function x of t, which is phi of tb. Okay, be the solution of x prime equals to f of x. Yeah, we just assume. Now, since L is decreasing, now you see, so what I am doing is this, I am just starting with the trajectory. Trajectory is given by x of t. Here I am writing it as a phi, doesn't matter, but basically it is x at t. Okay, so since L x is decreasing along the trajectory, along any trajectory, right? That's what is given, along trajectories of 1. Okay, what do we have? L of x of t gets dominated by L of x of 0, which is dominated by alpha. What is L of x of 0? See, L is decreasing along the trajectories of 1, non-increasing essentially, not decreasing, it should be non-increasing. Okay, so you see at the point x0 it is B star, right? See, this thing, oh sorry, I have to write x0 equals to B star essentially. So at the point x0 it is B star. Okay, L sorry, what am I doing? One second. Oh, I'm sorry, by mistake this. Okay, see, at the point x0, see, it starts from 0, right? And t is increasing. So at the point 0, this is x0 and let's say this is x of t. Okay, so along the trajectory, as the particle moves along this trajectory, L is decreasing. So at this x0 point, the value of L should be less than greater than the value of L at xt, right? Yeah, so that is what I wrote. So L of xt is less than equal L of x0. Now what is L of x0? L of x0 is nothing but this B star, right? Okay, so x0 is so this, now I should write it. You see, this along this trajectory, I have to write it here. I forgot to write it. See, the thing is, the trajectory, the equilibrium point is B star, right? So x at the point 0 has to be B star. That's the starting point. Okay, so and L at the point B star is dominated by alpha, so L at the point x0 is dominated by alpha. Yeah, is it okay? Right. Now you see, the thing is, this actually is a problem. You see, thing is, if this is true, alpha is the minimum of Lx on this compact set. Again, L of xt is strictly less than alpha. Is it okay? So the thing is this, x of t cannot cross the boundary of the ball with center B star and radius delta. That is clear, right? See, L of xt is always strictly less than alpha. right? And alpha is the minimum of L of x. So if it crosses somewhere, if it touches that ball, if it touches this ball, in that, at that point, it has, the value of L has to be greater than equal alpha, because the minimum is alpha. Okay, but here we have the xt for any trajectory xt, L of xt is strictly less than alpha. So basically what I'm saying, what we actually showed is this: the trajectory gets trapped inside this ball, right? That is the trajectory. So if I'm starting with the trajectory, you see this is some trajectory. Okay, the trajectory is confined uh, on the compact set, what is the compact set? B sorry, the ball with radius center V star and radius delta, the closure of that. Okay, but you remember we talked about this property long time back, right, while talking about the, you know, the maximum interval of existence, right? That if you have a trajectory which is confined on a compact set, okay, then what happens? The solution, therefore the solution exists for all time t greater than 0. Okay, moreover we can say that xt is containing the ball with radius b star, center b star and delta radius part, which is containing v. That's what we assumed, right? And then this actually shows that b star is Lyapunov function. So this implies that b star is Lyapunov stable. Okay, I hope this is clear to you. You see, you remember that theorem we did, right? We proved that if there is a trajectory, and I told you this is a way, at that time also I told you it is a very, very important theorem which we are going to use later also. So the thing is, if you can actually bound a trajectory in a compact set, then what happens is the solution, that will actually imply that solution has to exist for all time t. Is it okay? So since it exists for all time t, so x of t is in that compact set which is again contained in V, right? Okay, and that is the definition of Lyapunov stability. Then that will actually imply that B star is Lyapunov stable. So if you start with any, you know, you see, if you start with any solution, what is happening is this: for all time t, the solution exists, right, in the neighborhood of B star. So it is Lyapunov stable. Fine. Now the thing is, they see here, as I told you, the strict minima is very, very important. Okay, so let's take this example. See, remark: strict minima of L of x is necessary. Okay, it's a very, it's a essential this thing, requirement. What's the, so basically if we have to show that this is necessary, we have to give a counter example, right, or an example. So let's say, consider this system: x prime equals to y prime equals to minus x, this system. Okay, clearly the origin is a equilibrium point, it's the only equilibrium point. 0 0 is the only equilibrium point, is it okay? Now you see, L of xy, if you want to define as y square, okay, that satisfies condition A. You see, this condition is, which is condition A, that decreasing, this one. Yeah, so you can easily check this part, that's trivial, there's nothing to do here. Okay, so please check that part, it is there. But the thing is, yeah, and has a minima at 0. minimum at 0, right? At 0. Okay, but you can check, but the equilibrium is unstable. Okay, so what happens is, and how do you prove it? Please look at the eigenvalues, you can check. So check this part. It's a this thing, constant coefficient linear system, right? You can of course write down what the matrix A is and check the eigenvalues, and then you can see that the equilibrium is unstable, right? So if both are negative, then you have a stable equilibrium. So basically it is an unstable equilibrium that you can check, and that is why the thing is, even you see here Lxy equals to y square, okay, that has a minimum of 0, but the minimum is not a strict minimum. Okay, so and what happens is this, in that case the theorem does not hold and the equilibrium is unstable. Is it okay? Right. I hope you understood why it is a strict minimum, right? It's a two-dimensional thing. So y square, so it is 0 on the whole this thing. Y equals to 0, so x axis, right? Okay, right. So now the next theorem which we do is this. See, the next theorem. See, first of all, what did we show? We showed that if you have a Lyapunov function, the system is stable. Is it okay? Just finding a Lyapunov function is fine. Yeah, it's stable. Okay, now the thing is this, and we have assumed that okay, strict minima is required at that equilibrium point, but we also assume this. You see, it is less than equal 0. So along any trajectory, the Lyapunov function is non-increasing. That's what we have assumed. Now what happens if it is strict? If it is strictly decreasing, is it okay? So basically we say in that case we call L is a strictly Lyapunov function. So maybe I can write it here. Okay, L is strictly, we say it's a strictly Lyapunov function. Lyapunov function if all conditions hold, if all conditions of Lyapunov function holds except the condition A, okay, except A. So except one has to change the following. So what did the first condition, gradient of L of x acting at f of x, that should be strictly less than 0. Is it okay? Once this is there, then we have, see, earlier case it was less than equals to, right? So it is non-decreasing, so non-increasing, sorry, yeah. But now I want this to be strictly decreasing. Yes. So now the theorem says that if the equation x prime equals to f of x admits a strict Lyapunov function. Strict Lyapunov function, you can actually guess what is going to happen, right? Near B star, then the equilibrium is asymptotically stable. Equilibrium is asymptotically stable. Asymptotically stable. Okay, so just Lyapunov function, just the existence of Lyapunov function guarantees that it is stable. The existence of a strict Lyapunov function guarantees that it is asymptotically stable. Okay, so let's look at the proof. See, the thing is proof. Now, by the earlier theorem, what we have seen is this. See, if the trajectory x of t starts near B star, then for all positive time it stays in that compact neighborhood of B star, right? That's what we proved. Yeah? So, by the previous theorem, theorem one has that if the trajectory, any trajectory, doesn't matter, trajectory x of t, it starts near b star, okay, then it exists for all time t, all t greater than equal 0, is it okay, and stays in the compact neighborhood, and stays in a compact CPT, compact neighborhood, NBT neighborhood, okay, compact neighborhood of B star. Yeah, if you remember, this is what we proved here. You see, this is what we proved. Xt cannot cross this, so the trajectory is confined on the compact set this, and this set is contained in V, right? Okay, so that's what I wrote. Okay, see, now what we do is this. Let's say that, see, for stability it just have to be in the neighborhood of B star. It cannot move away from B star. That's the point. For asymptotic stability, it has to converge toward B star. Is it okay? Right. Now let's see that so suppose it does not converge to B star. Okay. So suppose such a trajectory okay, does not converge to B star, does not converge to B star. Is it okay? Now then what we have is, we can have then there exists a sequence Tn, okay, which tends to tends to infinity. So you have a sequence with tending to infinity such that x of Tn is bounded away from B star. Is it okay? So basically you have a sequence here which tends to infinity such that x of Tn, okay, is bounded away from B star, because if it cannot converge to B star, it should be away from B star, right? So we can write it like this. Okay, so now what we are going to do is, we are going to invoke the compactness, and we will pass to the subsequence if necessary. Okay, so without loss of generality, what we are going to say is this: let x of Tn, okay, has a limit, okay, because it is bounded, right? X of Tn is bounded. Bose-Einstein theorem, bounded sequence, convergent subsequence. Okay, so up till subsequence I'm just writing x of Tn, I'm not writing up till subsequence. Let's say that converges to B, okay, for some B which is not equals to B star. See, it is away from B star, right? So it cannot be B star if it converges. Okay, now you see L is continuous, given the function capital L is continuous. Okay, so L of x of Tn, the limit n tends to infinity, okay, this will be L of B, continuity, right? Continuity of L. If x of Tn converges to B, L is continuous, so L of x of Tn has to converge to L of B, right? And this is nothing but limit t tends to infinity L of x of t. This is definitely true because x of t is a decreasing function, right? Since x of t is a decreasing function, sorry, L of x of t, so basically L is decreasing function. Is it okay? Right. Now the thing is this, see that now you consider the initial value problem. So consider x prime equals to f of x and x at the point, let's say 0 is b. Okay, and let's write the solution, and the solution to be, how do I put it, let phi sb solves the problem. Let's say, let's call this problem as 2. Solve the problem 2. Is it okay? Now see, since L is a strictly Lyapunov function, yeah, so for any S positive, see S is the parameter, yeah, for any S positive, L of phi of S is dominated by L of phi of 0b. Yes, see, L is strictly decreasing, so for a positive S, what is happening is this, L will decrease. Clear? Okay, now the thing is, and that, what is phi at the point 0b? It is nothing but phi at the point 0b is b, so this is nothing but L of b. Is it okay? Again, if you look at this, see, phi is continuous. See, phi solves this problem, so phi is continuous. Okay, therefore phi of SB is nothing but limit n tends to infinity phi of S x of Tn. I can write it like this. See, xtn converges to b. Since phi is continuous, I can write it like this, right? Yes. Now the thing is this. See, these you have to understand this thing. What is happening is this: phi of x s Tn is nothing but x of Tn plus s, right? Okay. So this is nothing but limit n tends to infinity x of Tn plus s. Is it okay? So what is happening is this: limit n tends to infinity x of Tn. You understand what I am saying? See, if you start from b, so basically it is saying that x of Tn as the n tends to infinity, that goes to b. Okay, so if you are starting from b, so basically means it is starting from Tn plus s. So basically you see, s equals to 0, what happens is you are at x of Tn, which at the limit goes to b. So that is why it limit n tends to infinity x of Tn plus s is nothing but phi of x of Tn. Is it okay? Right. So what happens is this: L of phi of SB, I can write it like limit n tends to infinity L of x of Tn plus s. Yes, this property is also called the semigroup property. This is also called semigroup property. Group property. Okay, so we are just changing the initial data. So the point from let's say x0 to x at the point Tn, that's what I am doing. Okay, so that is limit n tends to infinity L of x of Ts, which is nothing but L of b. As you take the limit inside, because L is continuous, x is continuous, we can take the limit inside. So if you take the limit inside, it's nothing but L of b. Okay, because of this, see, because of this we can write it like this. Is it okay? But you see, this actually contradicts this one, right? L of phi of SB is strictly less than L of B, and here I am showing that L of phi of SB is equals to L of B. So that's a contradiction. What does that imply? It implies that it has to. So basically what it is saying is it cannot stay away from B star, it has to converge to B star, provided this strict equality. See, here this strict inequality is important. Okay, that's why we have used it. Is it okay? Now what we are going to do is look at one example of how to calculate Lyapunov. So basically how to construct a Lyapunov function. Let's look at that example. Okay, so first of all, so the question may look like this. So investigate the stability of the following system. Okay, what is the system? Let's say x prime of t equals to minus 2x of t and y prime of t equals to x of t minus y of t. That's a system, right? Okay, now the question is this: we need to see whether this system the zero solution. Of course, zero is the solution of the system, right? If you look at it, you see the equilibrium point is 0, 0. So 0 is the solution of the system. Now the question is this, whether 0 is a stable solution or not. Okay. So the question is the zero solution, let me put it this way, zero solution, you do realize it's 0, 0, right? Zero solution stable. Okay, zero solution, what I mean is xt yt is identically equals to 0, 0. That's the solution, this solution. Whether this solution is stable or not, that's what the question is. Okay, now we have to find a Lyapunov function. What you do is this. See, generally speaking, most of the times the Lyapunov function has a very, the structure looks very much like same, like this. See, the thing is, we'll define L of xy to be alpha times x square plus beta times y square. In some cases, it can be alpha times x to the power 4 plus beta times y square, or alpha times x square plus beta times y to the power 4. You have to, how do I put it? You have to play around with these coefficients and see what works for you. Okay, right. Now the thing is this, you see, of course you do realize that this is greater than equal 0. Okay, and it is only taking 0 at origin, with 0 only at origin. Okay, so you see, at the equilibrium point, an origin is equilibrium point of the system. So basically at the equilibrium point, this function, the function has a minima, okay, which is essentially 0. Okay, and everywhere else this is positive, provided alpha and beta are positive. Yeah, so provided alpha and beta are positive. Is it okay? Now the thing is this, we have to find what alpha and beta is. Yeah, now you see, to do that I have another property, right, that it has to be strictly non-increasing. Okay, so I need to have ddt of L of xt yt. This property is there, right? Strictly less than 0. If you remember the second, this is the second property, right, or the first property. I don't remember which one I wrote, first or second. One of the properties, first property. Okay, the first property. This property has to be satisfied, right? Okay. So how do I show this thing? So see, it is nothing but this is nothing but dl dt, right? Dl dt. I don't want to write xt yt all the time. So this is nothing but chain rule, dl dx dx dt plus I should write it as del because this is a del L del x. See, A is a two variable function, so basically by chain rule it is gradient of L at the point xt yt and then y prime and then x prime t y prime t. That's what it is, right? You understand? So but I can write it like this also, y dx dy dt. So this is the same thing, right? Dot gradient of L is this and this, and then x prime and y prime is this and this. So if you take the dot product, this is what you are going to get. Okay, so you see, if we write it everything properly, it is 2 alpha x minus 2x, right? X prime t is minus 2x plus 2 beta y, and then y prime t is x minus y. Okay, so this will actually give us that minus 4ax square plus 2bxy plus minus 2by square, right? That's your del y del dl del t. And this you can write it like this, you see, minus 2b, let me write it like this, it is 2a by b x square minus xy plus y square. Is it okay? Yeah. Now you see, if we choose, see, a and b is on us, right? Yes. So if we choose a equals to 1 and b equals to 8, let's say, this is not a, you do realize that you can change it also. If you do that, then dv dt, okay, will look like minus 16 times x by 2 minus y square. Okay, you just put everything together, this is what is coming out to be. Okay, and then this is strictly negative. Yeah, so if it is strictly negative, that will imply that 0 0, this solution is asymptotically stable. Not only stable, it is asymptotically stable. Is it okay? Asymptotically stable. So basically the whole point is you have to find a Lyapunov function, that's all. Okay, so in the assignment also we will give different how do I put it, other problems also to for you to find the Lyapunov functions. Okay, so what we are going to do is we are going to finish this particular video with the last part, which we are going to call the Lassalle's invariance property, invariance principle. Okay, so what does it say? Let's just understand this thing. See, what it says is this: if you, let's look at this particular system. So consider x prime equals to y and y prime equals to x minus x cube minus beta y. Okay, and beta is positive. Let's consider this system. Let's just call this system as 3. Yeah, this equation is called the Duffing's equation. Duffing's equation. Okay, please check this part, that these are the equilibriums. There are 3 equilibriums: 0 0, 1 0 and minus 1 0. Okay, these are the equilibriums, okay. Yes, and I mean, it is possible for you to show that plus minus 1 is asymptotically stable. Okay, you can do that. So and plus minus 1 are asymptotically stable. Maybe what you can do is use stable manifold theorem, okay, to show that plus minus 1 is asymptotically stable. That you can do. Yes, please do that. Now the thing is this: we want to use Lyapunov. Let's just see that since it is asymptotically stable, we can also use Lyapunov to do that, right? Okay, so if you do that, so what can we do is we can propose a function, let's say L of xy. Okay, what I am trying to say is this: see, plus minus 1 is asymptotically stable. How we know it? You can actually, so please check this part, check this. So we can actually use the stable manifold theorem to do that. But for now, let's say that we can also look at this thing Lyapunov, right? Let's do that. So let's construct this function L of xy, and for now let's just propose it like this. This is the energy function, they say, minus x square by 2 plus x to the power 4 by 4. Okay, this particular function. Yes, now you do realize that plus minus 1 0, this is a strict minima. Yeah, I hope you know how to find how to show that. So please check this part also. It's very easy to check, nothing special here. And you see, dE by dt, if you consider this thing, this is nothing but minus beta y square, right? Yes, so again you have to check it. So this is again strictly less than equal 0. So E is indeed a Lyapunov function. Okay, therefore E is Lyapunov function. Okay, but the thing is, see, d dt is strictly less than equals to 0. So basically what happens is, if you want to use the Lyapunov theory, it can actually give you up to stability. It will not tell you that it is asymptotically stable. You understand? For asymptotically stable, you need to have this one as strictly negative. Is it okay? So therefore theorem 1, theorem 2, let's say theorem 2 will not guarantee asymptotic stability. Huh? The only guarantee which you can get guarantee is stability via theorem 1. Is it okay? Huh? But the thing is, we already know that it is asymptotic is stable, so we are missing something. You understand? Yeah, we are missing something. So what can we do? Let's see. So these sort of situations are very fairly common actually. Yes, and we can use something called a Lyapunov. So this is this thing, the Lassalle's invariance property principle. So this actually I mean, how do I put it? If you have somewhere that a Lyapunov inequality that it fails to be strict, in that case you can use Lassalle. Is it okay? So what is this? It says that, let's say, that define a set S. Okay, what is this set? It is the set of all those x in omega 1 minus b star. Okay, such that gradient of Lx acting at f of x is equals to 0. Okay, see, in a Lyapunov thing, it is strictly less than equals 0, right? I need strictly less than 0 for asymptotic stability. So the 0 where it is becoming 0. Okay, so basically the trajectory is not strictly decreasing, but it is monotonically decreasing. Okay, so specifically it means, what does this mean? It means that no trajectory that starts in S, okay, remains in S for all positive t, all positive time t. This is what it means, huh? So sorry, this is what we assume now, for all positive time. Okay, so let's just assume this thing. This is our assumption. Okay, see, as we define this set, right? And now under this assumption we have this theorem. So this is Lassalle's invariance principle. Okay, what it says is this, and the proof, I am not going to do the proof. If you are interested, you please look at the proof yourself, you try to do it yourself. Okay, but the thing is, the theorem says this, that if near an equilibrium B star, okay, x prime equals to f of x has a Lyapunov function, okay, L, that satisfies this property, the earlier one. Let's just call it star. Okay, then B star is asymptotically stable. Okay, so it's not a very difficult thing to see. Basically what I'm trying to say is this: you just have to show, okay, that the thing is, if there is no trajectory, okay, see, the set S is there. S is where the trajectory is not, decreasing. Basically it is basically constant, it moves constant. So basically if it starts in S, it will remain in S for all time t, because it is constant, right? It cannot go down, right? L is not decreasing along the trajectory, so basically L is fixed kind of thing, right? So if along that trajectory, see, if it starts the trajectory, if it starts at that point, okay, it remains in that point, it remains on that set for all time t. If something like that happens, okay, if you have a trajectory for which something like this happens, then we can say that B star is asymptotically stable. Is it okay? So basically what we want is this: you cannot have a trajectory, no trajectory, okay, you cannot have a trajectory which starts in S, remains in S for all positive time t. Yes, see, it has to somehow leave S, because until unless it leaves S, it cannot be we cannot have the energy going towards zero. See, we know that at the equilibrium point, what is happening? If it is asymptotically stable, it has to approach the equilibrium point along any trajectory. You see, if you, let's say P star is the equilibrium point, if you move along any trajectory, the energy of the system is decreasing, and at the point B star, that is why the minima, we need the energy to be minima. The system along any trajectory, if you move, the system has a minima at B star. That's what it is saying. Is it okay? Now the thing is, that's what the idea of Lyapunov stability is. So basically, you see, along this trajectory, it has to somehow decrease, right, to reach B star, the minimum state, energy state. Now the thing is this: if it gets trapped in S, right, there is no way it can reach B star. Is it okay? So basically, what you need to do is, there is no trajectory. Yeah, if you can show that there is no trajectory that starts in S, remains in S, okay, for all time t, then B star is asymptotically stable. It's very easy. The idea, I mean, the intuition behind this is very easy, right? Okay, so the proof is not very difficult, but the thing is, it's kind of complicated. For now, what I'm going to do is, for this course at least, we are not going to look at the proof of this. Okay, so please remember that you can actually use Lassalle's invariance principle to I mean, compensate the deficit of Lyapunov stability, direct method. Okay, so with this I am going to end this video. I will give you some problems where you will see how to use Lassalle's invariance principle. Okay, thank you.